Hello there, Mr. Sutton here, bringing you the AB Calculus Chapter 6 Quiz 1 Review Solutions on differential equations. For this problem, we're given this differential equation here, and we're basically trying to find the original function if we have an initial condition of 0, negative 1. So we always look to see if we have the output variable in the differential equation. We do. We have y, and it's the output variable because it's dy over dx. Because we have the output variable there, we need to separate the variables so that the output variable gets to hang out with its differential. So we're going to start this one by dividing both sides by y minus 1 quantity squared. That'll give me dy over that, or we could write it as y minus 1 to the negative 2 dy, just so it's easier to take the antiderivative in a moment. Next, we're going to multiply dx by both sides. That brings it over to the right side with the x. And it doesn't really matter if there's an x over there or not. Really, we just need to get the dx so that it's on the other side. Now that we've got them separated, we're going to take the antiderivative of each side. On the left side, using the reverse power rule, this bumps up to a negative 1. Dividing by that, we have a negative quantity y minus 1. And on the right side, this bumps up to a 2. Divide by that, we've got 1/2 x squared plus c. Next, now that we've got the plus c in there, we need to plug in the initial condition to find the value of c. That's how we get the particular solution. So plugging in negative 1 for y on the left side, we got this stuff right here. And on the right side, we have 1/2 times 0 squared plus c. That 0 is going to get rid of everything except the c, so c just equals whatever we have on the left side here. And what do we have? Well, this is negative 2. And then raising that to the negative 1, that's going to be negative 1/2. But then this negative out here gets applied, giving us positive 1/2 for c. Next, we're going to plug that 1/2 in for c over here. And pretty much everything is the same, except that now we have to isolate the y value here, the y variable. So before I do anything else, I'm going to go ahead and just merge everything on the right into one fraction so that I can handle it all at once instead of having to distribute every single time. So this will be x squared plus 1 over 2. So not necessary, but definitely, I think, helpful in this situation. Next, we're going to multiply or divide by negative 1. So that's going to be y minus 1 to the negative 1 equals negative this fraction. Next, to get rid of this negative 1 exponent, I'm going to raise both sides to the negative 1. So that just gives me y minus 1 on the left side. On the right side, I'm just flipping this fraction, so 2 over x squared plus 1, still negative. And then finally, we add 1 to both sides to get y by itself. And this expression is our final answer. On this problem, we're given this differential equation here, xy over 2. And we basically want to figure out, first off, the particular solution with an initial condition of f of 0 equals 3. And then we want to use that to find the value of f of 0.2. So first off, do we have the output variable in the differential equation? We do. We have a y here. So that means we have to separate our variables. So for my first step, I'm going to divide y, both sides by y to get it over on the left. That'll be dy over y, or 1 over y dy. On the right side, I'm going to multiply by dx, giving me essentially 1/2 x dx. And now taking my antiderivatives on the left side, this is ln absolute value of y. Over on the right side, this bumps up to a 2. Dividing by that, we have 1/4 x squared plus c. Time to plug in my initial condition. So I'm plugging in 3 for y on the left side. On the right side, I plug in 0 for x. And that zeroes out everything except c on the right side, so I just have a c left over there. C equals ln of 3. I'm about to plug in ln of 3 for c, but before I do that, I have to resolve this absolute value here. We can't leave that kicking around in the particular solution. So to do that, I look at my initial condition, and I see that I have a y value of 3 initially. That means that the stuff inside here, which is just happens to be y, is going to be positive if y is 3. So that means we actually don't need the absolute value. We can just write this as ln of y. Now, if this had come out to a negative inside here, to simulate absolute value, we would have made this ln of negative y. But since it comes out positive anyway, we don't have to go to those extreme measures. Doing the rest of it now, we still have that 1/4 x squared on the other side of the equation, plus the c value we just found of ln of 3. All we have to do is isolate y now. I can do that by raising e to both sides. That will undo the ln. So we have y equals e to all that stuff. And we're actually done, but if you want to go one more step, you could essentially split this up into e to this first term times e to the ln of 3, and then e to the ln of 3 is just 3, so you could write all of this as 3e 1/4 x squared. Now we're not quite done with everything because they wanted us to find f of 0.2 using our particular solution. So to do this on the calculator, I've entered my particular solution into my y equals, and then I'm just going to do alpha trace, pull up y1, and plug in, they said 0.2. So there we go. That comes out to 3.030 if we take it to 3 decimals. On this problem, I've got this differential equation, which I want to solve for its particular solution, given an initial condition of g of 6 equals -4. So let's start by separating our variables. We have to do this because we have a y, an output variable, in the differential equation. I'll start by multiplying y by both sides. So I've got y dy on the left. On the right, I've got, if I multiply by dx, I've got 3 minus x in parentheses times dx. And now let me take my antiderivative. On the left, I have 1/2 y squared. On the right side, going term by term, this is going to be 3x minus 1/2 x squared plus a c. Let's plug in our initial condition now. For y, we've got -4. And for x, each of those is getting a 6. So 3 times 6 minus 1/2 times 6 squared plus c. On the left side, what's this come out to? Well, this is really 16 if we square it, times 1/2 is 8. On the right side, this is going to be 18 minus, let's see, half of 36 is also 18, also 0. So we just have a c then, which happens to equal the 8 that is remaining on the left side. Cool. Well, let's plug c back in. Now, there's no absolute values or anything else like that to resolve yet, so we just plug c in right away. And now we have to isolate y. To do that, I'll start by multiplying everything by 2. So that's a 6x minus x squared plus 16. Now I have to square root both sides. But normally when you square root both sides of an equation, you get a plus or minus. But we can't have a plus or minus. We're only supposed to have one branch for our particular solution. So we have to figure out, should y be negative or positive? To figure this out, let's look at the initial condition. In our initial condition, y is -4, which means in general, y has to be negative for this expression, for this particular solution. So that means if I have to choose between the plus or the minus radical all of this stuff, I'm going to go with negative radical 6x minus x squared plus 16. And there we are. For this problem, I have this differential equation, and I'm trying to graph the slope field for this thing on the axes below. I only have to graph it at 9 different points here. So what we're doing essentially is plugging in each set of x and y values to our differential equation, figuring out the slope, and then drawing a tiny little tangent line at each of these dots that represents that slope. So to make this easier, we're going to start with a table. And in my table, I have the x values -1, 0, and 1, because that's what we're using here. I also have just the y values 1, 2, and 3. And I've set my table up more or less in the same spatial way as these dots are arranged here. So starting up here, and I'm going to go row by row here, I've got, let's see here, this is the y value 3 times the x value -1. So 3 times -1 up here, or actually -1 times 3, because it's x then y, all over 2. That's going to be -3/2. Now I've got a 0 for x up here. That just gives me 0 no matter what else happens. And then I have a 1. So that's going to be just positive version of what we had there. And that's going to be the case throughout here. We're always going to get something over here and then an opposite version over here. So going on to the next one now, we have the x value -1 times a y value of 2 up here. So that's -2 over 2, which gives me -1. Anything times 0 is going to be 0, and then this will be +1 over here. Next, we have the x value -1 times a y value of 1 over 2. So that's -1/2. And then we get 0 and +1/2. So drawing these out, we'll start up here. this is going to be negative 3/2, so that's a slope of down 2 over 3, so something like that. Or actually down 3 over 2. Down here over 2, there we go. And then 0, we got just a horizontal tangent line. Now we're going up 3 over 2. So you could think of that as going like down 3 and left 2 if you want to kind of make a longer line and then shorten it up there to get that little tangent line. Next, we've got a slope of negative 1, 0, positive 1, and finally negative 1/2, 0, positive 1/2. For this problem, we're trying to get the slope field for this differential equation. So I'm going to set up a little table with all the x values from negative to positive 2 and y values going from negative to positive 1. So if y is 1, that's this first row here, we have 1 minus 1, which is just going to be 0. That gives us zeros all the way across here. So now let's go down to the next row where y is 0. If y is 0, then we end up with having, let's see, 0 minus 1. If we square that, that's just 1. So really, that's just going to give us whatever the x value is. So if the x value is negative 1, then negative 1 is our output. 0 gives us 0, 1 gives us 1. Down to the last row, we have a y value of negative 1. That's negative 1 minus 1, which is negative 2. Squaring that, we have 4. So it's going to be whatever the x value is times 4. So negative 1 times 4 is negative 4. 0 times 4 is 0. 1 times 4 is 4. Going across now and graphing out these tangent lines, this top row here is just all horizontal tangent lines because those are all slopes of 0. And the next one we have a slope of negative 1, then 0, then positive 1. And finally, we've got down here negative 4, very steep, 0, and positive 4. On this problem, we're trying to figure out which of these differential equations could represent this slope curve. So my strategy on these is just to pick a point on the actual slope field, see what the slope should be, and then test out that x and y value in all the answer choices to see which one matches that up. So I'm going to start by testing out the point 0, 0. The derivative of 0, 0 on our slope field here is actually dne. There's nothing there. So let me see what happens if I plug in 0, 0 for all these. So choice A, that gives us 0. That's something. Choices B and C are going to give us undefined, so that's still in the game. But D and E, those are both going to be defined. Those are real numbers. So we can eliminate A, D, and E. All right then, that brings us to testing another point because we're down to B and C. So I noticed that these are pretty much the same idea. We have one variable divided by another. So I'm going to make one of the variables 0 and see what happens. I'm going to test out the point 0, 1. I could have gone with 1, 0 also, but let me do 0, 1. Now in the slope field, that has a slope of 0. Let me see what happens when I plug in 0 and 1 for x and y in these two answer choices. So for choice B, this gives me 1 over 0, which is undefined. And in choice C, this gives me 0 over 1, which is very much defined, as 0 actually. So choice B then can be eliminated, leaving us with choice C. For this problem, I'm trying to match this slope field with one of these differential equations. Let me start by testing out one of the points on my slope field. I'm going to test out 0, 0. That's kind of my go-to point, and sometimes it doesn't help, but a lot of the times it gives me something useful because 0 is such a unique number. Looking here on my slope field, it's kind of hard to see, but there is a horizontal tangent line there, so that's a slope of 0. Looking at my answer choices now, if I plug in 0 and 0, that makes choices A, B, and C undefined. D and E both come out to 0, so I can't eliminate either of those yet. But A, B, and C are gone. All right, for my next point I'm going to test, I'm just going to try out 1, 0. We just got to try something else. We've got essentially two things being added and two things being subtracted. So pretty much anything you pick ought to be able to sort those out as long as you don't pick zeros for both of them. So if I pick 1, 0 in my graph, that appears to have a slope of maybe positive 1. I'm not really sure, but it is a positive slope. So I can at least use that information. Taking a look at choice B now, if I do 0 plus 1, that is positive. If I do 0 minus 1, in choice E, that's going to come out negative. So I can eliminate choice E because that does not give me a positive slope. So then choice D. On this problem, during the exponential phase, our E. coli bacteria increases at a number to rate proportional to the current population. Essentially, we're saying we have exponential growth if you do the diffie-q out for that. So we're going to start with y equals c times e to the kt. That's our exponential growth formula. If it were decay, we would have a negative k in there. Growth rate is 1.7 per minute. Current population 143.0 million. We want the population in 6.7 minutes. So we're looking for a target y value, and we're starting with an initial value, a c value of 143, and this is in millions now. We have a k value based off this percentage of 0.017 and a t value of 6.7. So plugging that all in, we just have to basically plug in 6.7 for t, and now just do it out on the calculator. So letting our calculator take care of the number crunching here, we come up with 160.252, and that's going to be million bacteria. For this problem, we have a savings account compounded continuously. The balance was this amount 5.5 years ago. Current balance is this. We want the annual interest rate. So we have growth because this is continuous compounding on a bank account. So we're going to use y equals c times e to the kt. And we're looking for the k value if we want the annual interest rate, which means we need to know all the other values. So we've got a current value. The current balance is $1,344. So we can put that in for c. And we also need to know the time and some other target value, some other value at that time. Well, they told us that our balance was $1,043.57 5.5 years ago. So I can plug in this number here for y, and for t I'm going to use negative 5.5 because this is 5.5 years in the past. All right, to solve for k now, I have to isolate the exponential term, so I'll divide both sides by 1344. And now to get rid of that e, to get these out of the exponent, I have to take the ln of both sides. So that's ln of this fraction equals, well, ln of v just cancels it out, so this is just negative 5.5k on the right side. All I have to do now is divide by negative 5.5. So if we do that division out on the calculator, we end up with about 0.046 and not a whole lot of change. So there's our k value. Now to convert that to an interest rate, we just multiply by 100 to express it as a percentage. So that's 4.6%.